Good evening, everyone. Welcome to today's problem solving section, week 10, course Digital Electronic Systems. We will start with the synthesis of sequential logic circuits, and first we will begin with the Moore model. So, the sequential logic can be either of type Moore model or Mealy model. So, we'll discuss briefly about these two models and how to synthesize the sequential logic of the equation and the implement. Let's start with the Moore model. And let us start with the Moore model. So in the Moore model, for any sequential circuit, we will have a combinational block, so a combinational logic as well as a memory element. And through the memory element, we have a feedback path. To the combinational input logic, we have input, which are also called as primary inputs, and we obtain the out so through some combinational logic, and this output is the primary output. And in the mode model, the output depends only on the present state. So we obtain the state output here, and this is the state. So affects the internal state. The input is affecting the internal state and not the output directly. The output is generated solely from the push memory. The memory is pushed up on the list, and out is synchronized to the clock. So the output is synchronized with the clock and is generated from flip flop or the register. And it depends only on the internal state. That is only the state, not on the input. Let's see one example. This is the example which we already see. This either acts as a up counter or as a down counter. If the mode is 0, counter, and when the mode is down, it acts like down. That is, let's see, this is here. Instead of this will be something here. That is, this one. This will be selected. This plus A bar and this will be 0. So this will be 0. Now let's draw the state diagram. So if we consider we are in the 0 0 state, we are performing the up counting. So we have not reached the final count value. Say the counter counts from 0 0 till 1 1, and when 1 1 comes, output is equal to 1. Let's consider this. That because output y is A and B. So when A and B are 1 1 only, y is 1. So now from this logic diagram, we are trying to draw the state diagram. When we have 0 as an input, that is the input is the mode select. It performs the up counting and output is 0. Again 0. It performs the up counting, output is 0. Now 1 1. A and B are 1. 1 and 1 is 1. And it performs the up counting. So next 0, it goes back to 0. Whereas now we are in this state. If we get M as 1, it will perform the down count, down counting, down count, and down counting back to 0 0 state. So in this way we can obtain the state diagram. Next, this is the Moore model. So for here you can see inside the state we are representing the output, and this is the state, as output only depends on the state, not on input. So here also you can see this is the output logic. Let me test this. It depends on this memory element and this memory element A, B. It is not connected to M, which is the input. So this is a mode measure. Okay. So next we will see Mealy model. So synthesis of sequential logic circuit and considering an Mealy model. So any sequential logic will consist of a combinational logic block which consists of primary inputs and primary outputs and a memory element which applies the feedback. This is the next state, inputs and the state outputs. So here you can see the primary output depends on the primary input also. So input affects the internal state and output directly. There it was affecting only the state, here both state as well as the output. So output is generated from flip-flop, generated from flip-flop and input. And output is not synchronized to the clock because it also depends on the input. So output is not synchronized with clock. and in say during the clock period, output may change if input changes. So this has one disadvantage, which is input transients or glitches may affect the output. That is, say we have an input to be always 0, and for a short period it goes to 1 because of some noise or power drop. So it causes some glitch, and that glitch it is in the clock period. So the output depends on the input state also. So instead of say output to be 1, it goes momentarily to 0, and this can affect the output. So this is a disadvantage. Before, it was not dependent on the input, only on the flip flops, that is a state of the flip flops. Therefore, it was not affected from the input glitches or transients. And this is the disadvantage of linear model. But it has lesser number of states that you will see in the when solving some of the questions. So let's see one of the examples. So this is it has an input X. Now you can see the output. It depends on Q bar. It depends on this part, which is X. So it depends on the input. So this is a Mealy machine. Next, what is this? It is Q XORed with X. And what is Y? Q bar and X. Now this is a this will have two states and say 0 and 1 are the states. Now when the input is 1, let's say previous state was 0, 1 and 0 output will be 1. So this goes to 1. But what is this is 1, that means this is 0. Okay. Initially, this was in state 0 before output was going to 1. This is next state. This is the value which we have. So this will be 1. That means 1 and 1. Output is 1. Next, when it is in state 1 and you are applying a 0. So this is in the state 1. 1 and 0. It remains in the state 1. Previous it was 1. So output this is 0. So output is 0. Now if you get 1 has the input. 1 has the input. 1 is the previous state. 1 and 1 is 0. So it should go to 0. And next, this is 1, right? So this is 1. It was 1 before. So this is 0. So this is 0. Now you are in state 0. In the 0 state. Previous state, it is in 0. So output is 0. Remain in 0. It remains in 0. So what is the output? This is 0. And this one was 0. So this is 1. So it is 1 and 0. 0. So output is 0. So you can see here the output the output depends on the input. And this means the primary input. Okay, so if there is any glitch, for example, and say this was 1, okay, I will have to leave this. So if there is a glitch here, say now the input is 0, for a short duration it goes to 1, this, and consider the Q to be 1, that is it's always in the 1 state. So this is the thing. Now output will be 0 because of one input being 0. It goes to 1 because of this glitch, and then it comes back to 0. So this is the input transients or glitches affecting the output. So next we will see Mealy model to more conversion. Next thing, let's before this let's draw one. Let's take one example, that is let's draw the synthesis with more model, and we want to do the problem statement is sequence detector and we want to detect 110. So we will design this using the Mealy model here, and here synthesis with Mealy model. Okay. So now let's start. We are in the state A. Output is 0 because we have not detected this any sequence. We get the first one. We go to state B. Still we are in the first one. So 0. Output is 0. This is the Mealy model. So inside the state we are writing the output. Next we get one more one. So we go to state C and the output is still 0 because we have detected 1 and 1. Now we are detecting a 0. So it goes to a state where the output is 1. We have detected 1, 1, 0. And then if it gets another 0, it starts to detect, so it continues from the initial state. And initially itself we get 0, then we will wait in the same state till we get 1. Here if we get 1, 0, so sequence is disturbed, so we'll get back to the initial state. And from here if we get 1, then we will wait here till we get 0. So it's like 1, 1, 0, okay, 1, 1, 1, 0. Here we have the sequence, so we have to wait till we get another 0. And from this, if we get 1, that means 1, 1, 0. Again, we got 1, 1. So we have to wait for another 1 and 0 to complete the sequence. So we will go to this state, and when the input is 1. So this is called as the what we are drawing is called as the state transition diagram. Next, for the same sequence, we are using a Mealy model. So we are in the state A. Output depends on the input. So we are not writing the output inside the state. We get the first one. We go to state B. Output is 0 because it's the first one. Next, 1, 1. We get a 1. Output is 0 because sequence directed is 1, 1. We are in state C and we get 0. We go to state A. Now we have directed 1, 1, 0. So output is 1. Now in the initial state, if it is 0, then we have to wait in the same state with output 0. 1 and 0. Its sequence is disturbed, so we have to start from the first. And here, if we get 0, it is output is 1. 1, 1, 1 means we have to wait for 0 because we want 1, 1, 0. So it's, if we have to wait in the same state, if we get 1, so you can see that one state is lesser in the Mealy model, so the complexity is lesser, but output depends on the input, so the input glitches and transients are also making the output to change. So any doubts? So next we will go for Mealy and mode conversion. So if we have a Mealy model, say A and say some inputs T, then 0, 0, current 2, 2, 0, 0, and 1, 0, 2, 3, and 0, 1, 1, 0. Going to do, and this is going to say something four. Now, this, if we want to convert this Mealy model to more model, you can see that output of A is always 0, 0, 0, 0. So you can write in this inside. For the B, output is 1, so you can bring it inside, and output is given on the state and transitions due to 20. So you can write like this. And there is another transition one, which is for people. So in this one, there was no difference. We were directly converting. Now let's take another Mealy model. Let's consider two states. And this is 0, 1. Output is 1. Let's take this also same. Now let's bring change here. This output be 1. Now A has more output. 0 as well as 1. It depends on 2, 3, 2, and 1. Now to convert this to more model, the first A, let it be A1 when the output is 1. Next, let's break that A to A2 where the output is 0. B is having only one output, so let it be B. Output is 1, so B 1. Next, from T1, it was coming to the state A, and T2 and T3, 1 and 0. It was to the state A2. Next, from A, it was going for T4 state, then input was 1. Same way, this also should be there when it was 1. Next, when it is 0, it is coming to state B. This is coming to state B as well as this is also coming to state B. So in this way, we can convert a melee to more. Let's increase it a little bit, bring in more changes in the melee model. Let's take A. So let's read underline and let's have a loop 0, 0, 1, 1, 0, 0, 0, 3, 3, 3. Now let's convert this into a more model. So A with 1 have the output 1. And next we are breaking the A to A2 where the output is 0. And B is having output 1, so we can have only 1. Next, from T1, if input is 0, is having 1 as output and 0. From T2, it is 1 and T3 is 0. Now this loop, self loop, when it is having an input 1, the output is 0. So we can't put a loop like this here because its output is 1. Correct? So we have to bring this to this state when it is 1. Here we can put a loop, 54 loop, when it is 1. Next, when it is 0, comes here, when it is 0. Any doubt? Now, let's go for a synthesis example. Now we have seen how we can convert a melee to mode model or mode to melee model and seen the example. So I'm drawing the previous example, the sequence vector, which is getting 1, 1, 0, and the this is melee model. Now let's convert to mode model as per the previous example. So now the first, we have to break A has A1 and output is say 0. Okay, 0. Next, A2, here the output is 1. Next, B has output 0 only, so no problem. What about C? 0, 0. C also has 0. Only A is having output both 1 and 0. So we have broken that A value. Now, self loop, this loop. Output is 0, so I can put safely here when it is 0. Next, when it is 1, it goes to state B with output 0. When it is B0, it goes to 0. Output is 0. So 0. Next, from B, when it is 1, it goes to C. And when it is in C, 1 means is 0. When it is 0, output is 1. When output is 1 and you apply a 1, you have a transition to B. This one. The same transition should be here. And this transition, when you get to 0, it goes to back where the A output is 0. That transition. Okay, so we have used the conversion rules, conversion method that we have seen and converted this media to mole model. Next, let's consider an example of a Moore machine and let's start. So let's start with the state assignment. So considering that we have n states, the number of flip-flops is actually 0 log 2 n, and this means of log 2 n. So this is a sequence reductor of 100 110, sorry. Sequence reductor inducting sequence 110. Next, we have to assign a state value for that. So we need 2 flip-flops because this number of states are 4 and 2 log is, so we need 2 flip-flops C and D. Next we have 4 states A, G, T and D. We can assign directly binary value 0, 0, 1, 1, 0, 1, or an alternate assignment. Say I want only one flip-flop to change. So let's give a try assigning it in a gray code way. So states are A, B, C, and D. Let's gray code them. This gray code means 0, 0, 0, 1, 1, 1, 1, 0. You can see there is only one bit change, but there is a loop. Like the change from A to D to A. Again, D to A is one bit change only. So okay, fine, no problem. The next change is this loop, B to B, D to D. But this has 2 bit change. So the assignment, which is to you lesser hardware, also in terms of the hardware as well as the number of bit changes, we will get to know once we draw this the state assignment from the state table. You can choose the optimal assignments. So we will go with this assignment, and this is the our state transition diagram. Now let's fill this more model state table. So the present state, if it is 0, 0, the input 0, the next state goes to, we have assigned this as 0, 0, 0, 1, 1, 0, 1, 1. So it goes to state 0, 1. And in the 0, 0 state, if we have 1, it remains in the 0, 0 state. No, sorry. If it is 0, it remains in the same state. If it is 1, it goes to 0, 1 state. So we have, these are the 4 states. And let's have the input 0 and 1 combination. Now let's fill. 0 1 input 0 goes to 0 0. 0 1 with input 1 it goes to 1 0. 1 0 is input 0 1 1. 1 0 input 1 1 0. 1 1 input is 0 0 0. 1 1 input is 1 it goes to 0 1. What is the output? For which state output is 1? For the state 1 1. 1 1 only output is 1. Other states output is 0. Now, if we want to use a JK frequency, okay, then the excitation table of JK frequency. Zero 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 one 1 0 1 this 0x 1x x1 x0 0 0 0x 0 1 1x 1 0 x1 1 1 x0. Yeah, it is correct. Now we have to see a n plus 1 and fill JK and bn plus 1 to fill JB. Now let's fill 0 0 I'm filling B 0 0 0x 0 0 0x 0 1 1x 1 1 x0 again 1 1 x0 1 0 1 0 x1 and x1. The next a and plus 1 0 0 0x 0 1 1x 1 0 x1 1 0 x1 0 1 1x 0 0 0x x1 x0. So with this, we'll fill the KMRF and simplify the equation to obtain the inputs for JB, 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 JB. Next, design equations. X, Bn, A. From here, you can see, let's fill for JB. From this part, it's 1, x and 6, 4x. So it's JB. From the JB. JB is equal to x1 Bn plus xbn dot. Respect for KB. This one is 0. And those are excellent. Divide and the seconds. Let's write for K. X1 plus B and 1. Now let's fill for the output. So can you please tell me how many variables are required? The variable K1 is required for the output. That one down. So how many variables K1 is required? What are the inputs? A and B are the inputs. It is not input on the sorry, A and B are the subtractants. This is not input on the input. X will not come in the K-map. So only A and B and so it's a two variable K-map. So Y is A and B and so flip-flop. So next to this we will see the circuit realization of this model. So this is the circuit realization and the equations that we have obtained JB is X AN and KB is AN, JA is X bar DN plus X DN bar and KA is X bar plus DN bar and Y is AN DN. So here you can see it is BN. It is coming from here, so AN and JA is this is what this is BNB and this is X bar, so BX bar and this is X B bar, so X B bar. So you got the J value, correct? X bar B plus X B bar. What is KA? This X bar or the with B bar. Got the field. Next, what is JB, A and X? And what is KB? It's a A. Okay, so this is the circuit realization and A and BN or output. And you can see it's depend on the A and B, not on the X. So it's a more model. Okay, next we will see a example for the Million model. So the state assignment and the state table. State table. Yeah, state table. I have exact. We know it's log that seal log 2 and number of states are 3. So this is seal of 1.585 and this gives 2 flip-flop. So we need flip-flop B and A and states. We have only 3 states A, B and C. So we can assign the incidents 0, 1, 0, just the binary assignments. And let's proceed with this for the state table. So for this also, let present state be 0, 7, input can be 0, 1. 0, 1, input can be 0, 1. 1, 0. So what is the next state? 0, 0, input is 0, 0, input is 1, 0, 1, 0, 1 with input 0, 0, 0, 1, 0, 1, 1, 0 with input 0, 0, 0, and 1, 1. You can see always whenever the input is 0, it's going to this state. It's interesting. Yeah. Next, what is the output? The output depends on the input also. It is one, only one, this particular one. So rest is zero. Next, excitation table of JK flip flop. Here, PM plus 1, JK flip 0, 0, 0, 1, 0. That's 0x, 1x, x1, x0. So 0, 0, 0x, 0x, 0x. Here it is 0, 1, 1x, 1, 0, x1, 1, 1, x0. Next 0, 0, 0, x, 0, 1, 1x, 1, 0, 1, 0, and again 1, 0. Then 0, 0, 0, 0. So this is the state table. In the state table from the state transition diagram. Now let's simplify the expression and we'll see the logic circuit. So it's having two states as shown here. 0, 1, XX, XX. So JB is XAN. JA, it is X Boolean bar. KB is X bar. And this is all 1 or 1 and don't correct. So KA is 1. Next the output. So here the output is a 3 variable PMRF because this is a Miller machine. And X is the input is impedance. Original. Y is X bar depends on X. Let us see the circuit realization. The equation that we obtain JB is X element, KB is X bar, and is X bar, Bn. Bn. This is coming from here, which is x bar. X bar. So output depends on the input. Next, Ja is x and coming from B bar. B bar. Next, K is 1. JB. This is x and AX. This is coming from X bar. So you can see this is the relay circuit representation. So now this is the same circuit for detecting the sequence 110. So you can see this is more complex compared to this circuit. So this is less complex compared to more modern based circuit. Any doubts? With this you will solve some questions. First question, which of the following statement is true? The output are synchronized with the clock for both Mealy and Moore circuits. So we have seen the for the Mealy it is affected because of the input also. So it's not synchronized with the clock. This is false. For Moore model, the input affects only the internal state and not the output. Yes, it is. Mealy, the input affects both output and the internal states. Yes, it's true. Because of that only we said it's not synchronized to the clock. The Moore is more sensitive to glitches in the input as compared to the Mealy model. This is false. It's a Mealy model which is more sensitive to the glitches in the input as compared to the Moore model. So 2 and 3 are only true. Next question. Which of the following statements are true about this following state transition diagram? As a sequence detector, the same gap is the initial state. The state diagram corresponds to Mealy model. Is it true? Can see the output is defined inside the state. So output does not depend on input. So this we can say it's a mode model. So this is false. The minimum 4 flip-flops are needed to implement a sequence detector. There are how many states? 4. So 4 statements log 2 seals which is 2. So we need 2 flip-flops. So we need 2 flip-flops. So this is also false. The logic detects the sequence 110 or whether it detects 100. So this is the question. So let's trace. First one, it goes to the next state. Next, after detecting a 0, it goes to the next state. After detecting a 0, it goes to a state where the output is 1. So it is detecting the sequence 100. This is false. This is true. The state B and C correspond to detecting the bit 1 and 1 0 in the input sequence respectively. So this state, we got 1. So this is detecting 1. So B is detecting 1, true. And the C is detecting 1 0. Yes, it's true. So 4 and 5 are true. Next, which of the following are yeah, now the question is which of the following represents the mode model for the sequence detector that can decode the bit sequence? Class 8 o'clock. 8 o'clock, Anna. 8 వరకు class NPTEL. Which of the following represents the mode model for the sequence detector that can decode the bit sequence 110? So the sequence to detect is 110. So the sequence to detect is 110. So we have to draw the state diagram or okay. It's a mode model. So we will start with 0. We detect the first one goes to output B with 0. Then 1, it goes to C with output 0. We have deducted 1 and 1. Next, we have to deduct 0 goes to state D, 0. Again, one more 0. Now, we have deducted another 0. We go to state D, output is 1. Again, with 0, we have to start over again. Okay, if we have 1, we can start from here. 1 is deducted. What is 0? We have to wait here for 1 to come. And here, if it gets 0, we have to go back to the previous state. And in C, if we get 1, we have to wait in C till we get 0. And in D, we have taken for 0 to get 1 instead of 0. So we got 1, 1. We have to wait for another 1. And this, we have completed 0 and 1. This is the diagram. So option D. Let's decode what are the states it is detecting. 1, 1, 0, 0. But why not A option? Because this is a Mealy model. Next, what is this detecting? 1, 1, 0. It is staying in 0. This means it's 1, 1, 0, 0. Output is 1. It's perfectly fine. We get another 0. Again, output is 1. But this is not the sequence that we want to detect. So, on this option. And also, this is a Mealy model. Next, this is a mode model. And why not this? Let's see what this sequence it is detecting. 1, 1, 0, 0. Perfect. It is transitioning from this, but when is the output This 1, 1. Here itself the output is 1. So this means it's deducting 1, 1, 0, not 1, 1, 0, 0. That's right. Not correct option is option B. Is it clear? Any doubts? Next question. Convert the following Moore model into a Mealy equivalent. This is a Moore model. Mealy equivalent Q0, Q1. No need to mention the output inside the state. So when it is having A as the input, it's going to state where output is 0. It's going to state where the output is 1. And this is going to state where the output is 1. This is coming to state where the output is 0. So this is the conversion of this Moore model to the matrix. And this is the initial state. 0, 1, 1. Why not B? It's 1. This is correct. This is wrong. So you can see it's coming to a state where the output is 0. And it's coming to a state where the output is 1. And the inverse, so not the B. This is fine. This is coming to a state where output is 0. And this is fine. This is also. So, here you can see Q1 and Q0 are changed. It's Q0, Q1. Q0, only there is a transition. Okay. So because of this, not this option. The correct answer is option A. Next question. The number of flip-flops required for the synthesis of sequential circuit with n states. This is floor, so not. And if we have n state, then we know log 2 n C will give the number of flip-flops. So option D is the correct answer. Next question. For the given circuit, if x is equal to a, then find the value of J, K, KB. But if x is A, this is B bar. So what is this? A, B. Let's write it. J, A, S, A, B bar. They are represented as BM. Let's not as BM. K, A is 1. So K can't be X. This two options are limited. Next, this is A, this is A. Okay, JB is not given in the options. Next, A, A bar, A bar. KB should be A bar, so not this. KB should be A bar. Next, what is the value of B and A bar? So B, A bar, or A bar B. So option A is the correct answer. A B bar is the J, K is 1, KB is A bar, Y is A bar. And as they are denoting with SBN, we will also denote SBN. The question is SBN. No, this is KB. Actually, JB is A. Next question. Consider the following state table. Which of the following statements are true? The state table corresponds to Mealy machine. You can see the state is in A, but output is changing with respect to the input. State A is the next state with 0. State is A with input 0. Fine. A with input 1. So you can see that output depends on X value. So it is a Mealy machine. So the number of states can be reduced to 5 states. The number of states can be reduced to 6 states. States D, E, F, and G are equivalent. State D and F are equivalent. So for this, we need to reduce this state table. Let's use implication table method to reduce this table. So this is the present state. Next state. Same state table, right? AAB, BCD. AAB, BCD. Yeah. So the same state table I have copied here. Let's the implication table. It's the lower triangle matrix. It's the this is the matrix. These are the diagonal elements. Leaving this diagonal elements, this lower triangular matrix. So we'll use it for the implication table. So first leave the A, B, C, D, E, and F. Next. So D is A, B, C, D. A, B, C, D, and E. Now you see A to B, outputs are same. So when AC is same and CD are equal, then the output can be equal. For A to C, 0, 0. So A, E, B, F. A, E, B and F states will be equal. Next, A and D. A and D. Outputs are itself different, so this is not possible. Next, A and E. A and E. Outputs are same. AC, AC, BD, BD. Next, A and F. Output is itself different, so they can't be equal. They cannot form an equivalent set. Next, B and C. Outputs are same, so C, E, D, F. Next is B with D. Output are different. Next is B and E. B and E. C, C, D, D. Output are also same. So this is an equivalent set. Next is B and F. Output is different. C and D. Output different. C and E. Output is same. So it should be C and E should be same, and D and F should be same. Next is C and F. Outputs are the same. Next, E and F output is different. F and D, B, B, A, A. So they are equivalent. E with F output are different. E with D and E with F. Yeah. Now you can see from this D is equivalent to F and D is equivalent to E. This A C equivalent A C. Okay. We can't predict. C and D. Okay. So first the next implication table will be we have to replace F with D, E with B. Then here side. B and F are they equal? This is B and F, right? So this can't be. Next D and F. This is possible with C and D. Okay, let's wait. Next B and D. D, D. This is B and D. So this is not possible. C and D. C and D. This is C and D. So this is also not possible. This is C and E. C and E. So this and this. D and F are already equal. This condition is already satisfied. But the next condition is C should be equivalent to E. So you can say this are also equal. This means it is equivalent to C. So D is equivalent to F. C is equivalent to E equivalent to B. So we have DF, CEB and A. So the reduced set I think this is an example. Let's solve that. So we have till G. I have not solved the question yet. We have just. I want to take this. This is just an example to show how the implication table can be used to simplify the expression. So this is a simplified expression, and okay, this is just the implication table. Now we will solve the actual. This is an example question. This is an example. Let's solve the actual question simplification table. So it is still G. So B, C, D, E, F, G. Next. So this is A, B, C, D, E, and F. From this, can the state table be little bit bigger? So that, yeah. B and A outputs are different. They can't from the equivalent set. A and C output is same, so it should be A, B, and D. Next, A with D, no. A with E, A with F, and A and G is also not possible as the outputs are different. B, C, B is having 0, 0. I think no other state is having the 0, 0. So it cannot be merged. It's a unique state. Next, C is having 0, 1. We are not checking with the A. So C with B, with D, E, F, G. It's different always. D with all these 4 can form. It's E, F, F, E, G, F, F, A, E, F, F, A, E, and F. G, F, F, A, F, F, A, G, F. So this is true. So G is equivalent to E. If G is equivalent to E, then this will be equivalent. So this is also equivalent. So D is equivalent to F. B is not equivalent to D, and D is not equivalent to G because A and E are not equivalent. A is not equivalent. A and G is also not equivalent. A and G is not equivalent. So these are the only equivalent set. So we have G, E, D, F. So A, B, C, D, E, F, G. So we have 5 states. Yes, we have 5 states, not the 6. So this is true, this is true, this is not true. State A, E, F, and G are equivalent. No. E. State E is equivalent to G. And D is equivalent to F not. They are not equivalent. D and F are equivalent, yes. Because D is equivalent to F, E is equivalent to G, we have seen. So that means option 1, 2 and 5 are correct. Any doubts? Next question. The following state diagram, which of the following pair of states are equivalent? To solve this, first we need the state table, then the implication table. So first we will draw the present state table, present state. Next state, x is equal to 0, x is equal to 1. Present output, x is equal to 0, x is equal to 1. So there are 5 states, S1, S2, S3, S4 and S5. So what is the next state when 0? S2, this is S4, S1, S3, S2, S4, S5, S3, S4, S5. 1, 1. Output is, I'm writing output. Now the implication table. S2, S3, S4, S5. S1, S2, S3, S4. So S1 and S2 output are different. 1 and 3, 1 and 3, S2, S2, S4, S4 output are same. So this is always equal. So S1 is equal to S3. S1 and 4, no possible. 1 and 5. If S2, S4, S4, S5 are equivalent. S2, S3, no. And this S2 is having some unique outputs, it's unique state. Next S3, S4, no. S3, S5. If S2, S3 and S5. S2 and S4 are equivalent. And S4 and S5 are equivalent. and 4 with 5 is 2 and 4. It's 2 and 4. No. So it's S1 equivalent to S. State 1 and 3 are equivalent. Okay. The next question. Given the state diagram in the following figure, determine the equivalent classes obtained using the implication chart. So before, okay, I don't have space. Okay. Before going to the implication chart, we need the table present state, next state, x is equal to 0, x is equal to 1, present output, x is equal to 0, x is equal to 1. So we have states A, B, C, D, E, and F. So from A to A, then B, from B to C and D, C to E, F, D to E, C, D, B, A. What are the output? When is the output 1? Only in this. Other outputs are 0. No. Here output is 1. Here also output is 1. And whenever the input is 1, so this is 0 always. And this is F. This is to D. And this is to D to A is 1. And the input is 1. Then for B, it is this. This is all. It is I made some mistakes. And this one, B is 1. For D, it is 1. For F, it is 1. So now with this implication table, B, C, E, F. A, B, C, D, and E. So A and B, this is A, E, A and F. This is not possible. A, C, B and D, not possible. No. C, B, D, A, C, B, D, A. So C and D, C and E, D, F. No. This is equivalent. So BBA is this is equivalent. This is not possible. So this D is equivalent to F. When D is equivalent to F, this is equivalent. And what about C and D? C and D, if these are equal, no, this can be equal, so this is equal. Next, A and C. Okay, this one, B and D, B, D. Okay, this one, C and B, C, C and B. This is C and B. So this can't be equal. So B and D cannot be equal. Therefore, A and B cannot be equal. So the equivalent set are DF, CE, A, B, AB, C, D, E and F. Yeah. So it is DF, CE, B and E. Next question. Consider a moon machine with 4 flip-flops, 2 input and 6 outputs. Determine the maximum number of transition arrows leaving and number of transition arrows entering the state. So there are 2 inputs. That means 2 to the power 2, which is 4 combination. So 4 transitions arrow, transition arrow leaving a state, and 6 outputs. So 2 to the power 6, which is 64 transition arrow entering state. So it is 4, 64. Next is ASM chart. ASM means algorithmic state machines. So the state transition diagram, though it is compact, it is unsuitable for describing larger state machines. So ASM chart is a flow diagram like representation to describe a sequential electronic circuit. So it has a state box, which is a square or a rectangle with state name and output. So output, if any, derived only from state, and something like this, which is called as the conditional box, conditional output box, and this is for the output derived from state as well as the input, so for the millimodel, and the conditional output box. Okay, I have written the function. Next, for the condition, the decision box. Say there is a variable value. Then what is it? If it is 1, then it is 0. If there are two inputs, we saw 2 to the power 2, 4 in, branches. So n inputs, 2 to the power n branch at each state. That's why it is complex. Even though it is a compact way of representation, it's not suitable for describing largest equation. Say if A is 0, there are two input it is dependent. So it will have 0, 1, 0, 0, 1, 0, 1, 1. So this is going to be, this again will have 4 branching out. So you can see, because of this, it is getting complex, right? So next we will see example of a ASM chart for a more model. For a more model. Let's consider the same sequence deductor of 110. So this was the this is our input and this was our output y. I'm just naming it as x and y. Now let's represent this flowchart. So the input is x and the output is x and the output is y. We will start. A is the state name, output is 0. Next, the conditional block. Now we have to check what is x. If it is 0, it goes back to A. If it is 1, it goes to B. It goes to B. Next, where the y is 0. Next, x, based on x, it is going to 0 or it goes to 1, where the y is 0, which is C, which goes to, which has again 1 and 0. With when it is 0, it goes to D. And here the output is 1. Again, we have to check what is the x value. If it is 0, it goes back to the initial state of A. If it is 1, it goes to B. If it is 1, it goes to B, right? This one. If it is 1, this is that. Goes to B. And if this is 1 from C, it goes to C. This is the ASM chart. Any doubts? So next we will solve some more questions. Deduce the type of flip-flop from the following ASM chart. So what is the value of B? If A is 0, B is 0, the Q is 1, the next state goes to 1. If A is 0, B is 1, Q is 1, the next state goes to 0. If A is 0, B is 0, Q is 0, Q plus is also 0. If A is 1, Q is 0, Q plus goes to 1. So which type of flip-flop is it? You can see this performing the reset operation here, right? Yeah, set operation, because output is going to 1, and here it is performing the operation of reset. Here you can see it's just retaining the state. So they have not given the operation for 1 and 1, so it can either be SR or JK. So going to the next question, which of the following statement is false in case A or some chart of more machine? State is shown in the state box. Yes, it is true. State is shown in the conditional box. We said it is for the Mealy machine where it depends on the input. So it's in the state box, not in the conditional box. Decision box has 2 inputs. Yes. So option B is correct. Is the false. So next question. Algorithmic state machine chart is composed of. It has 3 elements: state box, conditional blocks, and the decision box. State box, conditional output box, and the decision box. Going to the next question. Consider the following state table. Now we have to reduce this table using the row elimination method. Row elimination method means option D. Yes. This I'm just continuing. So D and A. D and A. This means this row can be eliminated. Next is C and D, C and D. So this row can also be eliminated. This means A is equal to N. We are in this row, which means B is equal to C. Now we have to replace C as B, F as A. So again DA. This row can be eliminated. And now this is equivalent to E. And BC. H is equivalent to this. So you can say A, F, E, and B, C, H, D, and G. Option D is the correct answer. So the next question, consider a FSM with the following state diagram. So what is the X and B denote the input and output sequence respectively. Find for the input sequence, the output sequence Y for the given FSM is assuming the sequence progresses from the left to right. Left to right means we start from this bit, we progress. So what is the output? First it is 1. So in this state, output is 0. Next is 0. This state 0, 0, same, remaining in the same state. 1, going to the state, output is 0. Again 0, going back to the state, output 0. 1 is 2, 0. 1 is 3, 0. Next is 0. So output is 1. 1 is 2, 0. 0, again 0. 1, 1, then again 0, 0. Yeah, total 13. So the answer is C. So next question. For the given circuit diagram, if AN is equal to 0, PN is equal to 1, I equal to 1, G equal to 1, what is the value of AN plus 1 and BN plus 1? So value of D, A, if you see it is J bar, I, it will be B bar and A bar. And here A, I bar. So it is A, I bar plus J bar, I, B bar, A bar. Next DB. It is B, I bar, J bar, A, B, J, A bar, I, B bar, B bar. So it is B, I bar plus J bar, A, I plus J, A bar, I, B bar. The next X. This is coming from J, I, A and this is B, I. So it is J, I, A plus B, I. Why is B, I, J? Because this is J. So next D, A is 1, 0 plus 0 which is 0. D, B 0 plus 0 plus again 1 and 0 plus again 0. X is 1 because A, I and J are 1 and then Y is again 0. So AN plus 1 and BN plus 1 will remain 0. X will be 1 and Y will be 0. Next question. The two states are considered equivalent if any move to the same or equivalent state for every input combination and generate the same output. So this is also true. This is true. Tautology means to the same condition that any two states A and B are equivalent if state A and B and A are equivalent. A and B should be equal, then B A should be equal. So yes, this is also so both A and B are true. Again, next question: which of the following statement is or are true? State transition diagram are more compact representation. This we have seen. Yes, it is compact. State diagram are better suited for representing problems with more number of inputs. If it is more number, then 2 to the power n. So it will become. It is not suitable. So it's false. Circuit realization using AL sum is different from circuit realization using. So both are the same representation. So only one is true. So next question. This is one of the previous year's gate questions. So can you try this question? Suppose we want to design a synchronous circuit that processes string of zeros and ones. Given a string, it produces another string by replacing first one in any subsequence of consequent one by zero. So this is one, it replaced to zero. This one is replaced to zero. This one is replaced to zero. A Mealy machine is a state machine where both the next and the output depends on the present state and the input. This we know. The above mentioned circuit can be designed as two-state Mealy machine. So we have to design using a two-state Mealy machine. Let's take this. For simplicity, I am assigning the state as 0, showing it here itself, state assignment 0 and 1. And then next, okay, they have already given Mealy machine with two states represented as 0 and 1. 1, 0. We denote the current state, the next state, and the incoming bit on the output. Okay, this will come. Assume the initial state is 0. So whenever it is 0, output is 0, it remains 0. And when it is 1, the 1 is replaced to 0. If it is 0, it retains to be 0. The next one is 1. So this is the state transition diagram. Next, with this present state, next state, no, we need input, next state, output. Output is represented by y. This I have given as t, b, b is the input, b is the incoming bit input, and s is the present state. So 0 with 0 input, 0 with 1 input, 1 with 0 input, 1 with 1 input. So what is the next state? It remains equals to 1. It comes to the output is 1 only in this state for the first occurrence of the 1. Now you can see what is t. It is just this. So t is b. What is y? It is s b. So it is t is equal to b, y is sb. So any doubts? So if no doubts, so we can complete today's session. Yes, thank you for joining. Thank you.